Right, let's get started. So hello everyone, this is Kim. So yeah, here this is lecture 11. So lecture 11. Here we discussed we introduced some concept. For example, inner product or length of vector or also corner vectors, something like this. And today we will discuss another very important concept, also corner set or also normal set. Okay. So last week, not last week, Tuesday. By the way, to check your midterm answer sheet, please check your TA session. 그쵸? Maybe today. I'm not sure. Let me check. 그쵸. 끝났네. 오늘. So everyone check your answer sheet. Everyone? Or who want to need further midterm checking? No? Okay, see, if you want to check your answer sheet further, please let me know. Then I will reserve the meeting with TA to check your answer sheet. Okay. Okay, let's move to the section. What? So Tuesday we discussed the inner product. What is the inner product? And also corner vector and one of the very important definition, two vector U and V in Rn space are orthogonal or perpendicular to each other if U inner product V equal to 0. And we can introduce Pythagoras theorem. This is theorem 2. The vectors U and V are orthogonal. Orthogonal if and only if the length of the U plus V. This is U plus V. Length of U plus V is equal to scale of the length of the U and plus scale of length of the V. Why? So from where's that? Yeah. We can easily prove this one from here. So this one is U plus V, scale of the length of the U plus V is equal to scale of the length of the U, scale of the length of the minus 2UV. But if U inner product V is equal to 0, then this one is going to be the Pythagoras theorem, right? So because UV 어디죠? orthogonal theorem. Not orthogonal theorem. Inner product U and V is equal to 0, then U and V are orthogonal. So you can easily prove the Pythagoras theorem. And one more very important concept is angle between the vectors. Vector U and V are non-zero vectors in either R2 or R3, then there is a nice connection between their inner product and angle theta between them. For example, let's say here is vector U and here is vector V. We are interested in the angle between two vectors. Then relationship between inner product U and V equal to length of the U times length of the V times cosine theta. So this is the angles between the vectors. So let's prove this one first. Here is the vector u, and here is the vector v. Let's prove. So first of all, by rule of the cosine, 그쵸? From your high school, rule of the cosine, scale of the length of the u minus v is equal to scale of the length of the u, scale of the length of the v minus 2 times length of u, length of v, cosine theta. 그렇죠? This is cosine similarity. If you are not familiar with cosine similarity, don't worry. So please check that this is cosine, rule of cosine. From here, we can rearrange to produce this one equals to 1/2 times this one from here, here, and here. It's very easy. And then because if, for example, if u is equal to u is in R2 space, or v is in R2 space, then we can rewrite this one as this one. 그렇죠? Why? We already know the length of this one is scale of u1 제곱 plus u2 제곱. 그렇죠? 그래서 we can represent this one looks like this. And if we summarize this one to this one, it's going to be u1 times v1 plus u2 times v2. It's going to be inner product uv. So the verification of for R3 is similar. It can be generalized. It can be used to define angle between two vectors in R3 in general. Okay. So this rule. So in other words, if we know inner product between two vectors, we can determine the angle between two vectors with this equation. Okay. Question. No? So this kind of the distance or the angle concept is in use in many application in computer science field. In fact, the deep learning field, I mean the artificial intelligence part or the computer vision part, this kind of distance concept is very usefully used. For example, this is just like the deep learning model. So if you are interested in this one, please try to watch the YouTube video or try to take a artificial intelligence course or the deep learning course. But anyway, so this is the image, and this problem is to answer this is a cat or non-cat. In deep learning, so given an image, we combo the input image with some black box layer and generate the feature vector. So for example, our N space, then we have ground truth or N space. Then we have to determine the similarity between the estimated one and ground truth one. Then by minimizing this distance, we can train this one. This is called the learning networks. Here, define the similarity. Let's say this is a vector y and this is vector let me say z. Then we have to determine the similarity between the y minus z. Looks like this. This is called the loss function. So anyway, so by minimizing this loss function, you can train your model. So then your model can say that this is a cat or non-cat. This is very, very simple examples in distance in deep learning. Anyway, so when you define this distance function, you can use the L2 distance, looks like this, or the dot product. Okay. Yep, this is the chapter 6.1, and we'll move to the chapter 6.2, orthogonal set. In orthogonal set, chapter 6.2, we'll use the so many concepts introduced in chapter 6.1 and discuss what are orthogonal set. Okay? Any question so far? 질문? Question? No? Okay. So, orthogonal set. We already discussed the orthogonal, right? What's orthogonal? Here, 그렇죠? Two vectors are orthogonal each other if inner product U, V equal 0. So what does it mean? If U, V is here, the two vectors are perpendicular, right? In this case, we say that this is orthogonal. Now, orthogonal set means a set of the vector U1, U2, and UP in Rn space is said to be orthogonal set if each pair of the distinct vectors from the set is orthogonal. That is, if Ui inner product Uj equals to 0, whenever I is not equal to 0, then we can say that this set is orthogonal set. Orthogonal set. Orthogonal set. For example, let's consider a very simple example. If a set have 1, -1, and 1, 1, then this set is orthogonal. Why? Because of this vector times this vector, it's going to be 0. So this is one of the examples of orthogonal set. And here's the theorem 4. If set S consisting of the vector U1, U2, and UP is the orthogonal set of non-zero vectors in Rn space, orthogonal set of the non-zero vector in Rn space, then S is linearly dependent. If S is orthogonal set and S is linearly independent, hence is a basis for the subspace spanned by S. Subspace spanned by S. Subspace spanned by S. Let's say subspace W means spanned by S means U1, U2, UP. This one. Then this one is going to be if this one is also orthogonal set, and this is the linearly independent, and this is the basis for the subspace. Let's prove this one. To prove this one, to say this one, to become S is linearly independent, C1 U1 plus C2 U2 plus CP UP, given this equation, only C1 is C1 C2, only case of C1 C2 CP equal to 0, then we can say that U vector U1, U2, and UP are linearly independent. Let's prove this one. Okay. So here, 0 is equal to C1 U1 plus CP UP for some scalars C1, C2, CP, C1, C2, CP. Then 0, it's going to be the 0 vector times U1. 그렇죠? 0 vector times U1 is still 0. It's going to be this one from here, from here, and U1 here. So C1 U1 plus CP UP inner product U1. So then by the properties of the inner product, we we can derive new equation as a C1 U1 inner product U1, C2 UT inner product U1, CP UP inner product U1, then C1 times U1 inner product U1, C2 times U2 inner product U1, CP times UP inner product U1. Then we already know this one is orthogonal set. So every vector each pair of the vectors are orthogonal. So we already know this one is equal to 0. And this one is equal to 0, and this one is equal to 0. Because you set 8S was the orthogonal set. Then 0 is equal to C1 times U1 inner product U1. Also U1 is orthogonal to this one. Since U1 is non-zero, since non-zero, 그쵸? By definition, non-zero vector, 그쵸? Since non-zero vector, U1 inner product U1 is not zero, 그쵸? U1 is not zero, so C1 should be 0 from here. Right? Similarly, we can derive for the U2 case, U3 case, blah blah blah. Then C1, C2, CP, C2, C3, CP must be 0. Then set S is linearly independent. Set S is linearly independent. This is the proof of this theorem. It's very, very clear. Okay. In other words, orthogonal basis. From now we can say orthogonal basis for the subspace W of Rn space is a basis for W that is also orthogonal set. This is almost the same thing. Okay. Question. So orthogonal set이면 항상 linear independent 하니까 얘네는 이 뭐예요? S로 스팬트된 subspace의 베이시스다 라고 하는 거죠. 자, 이거 왜 하느냐 뒤에서 좀 설명해 줄게요. 여기까지니까 이해를 해요, 여러분. 그렇죠? orthogonal set이면 베이시스다. 그래서 특이한 케이스로 어떤 subspace W에 대해서 orthogonal 베이시스 들어가는 거는 베이시스면서도 orthogonal set을 말한다 하는 거가 좀 이해해 주면 돼요. question. 따라오고 있죠, 여러분? Why do we have to study orthogonal basis for this theorem? Theorem 5. Let U1, U2, UP be an orthogonal basis for a subspace W of Rn space. Subspace W of Rn space. 그죠? orthogonal basis for each vector y in W space. Subspace, 그죠? W space. The weight in the linear combination. For this one, for y, weight is this C. Weight in linear combination are given by C for each Cj is equal to y inner product to uj over uj inner product to uj for each j. Very, very difficult, right? It's very, very hard to follow. Let me explain this one step by step. So please follow me. So first of all, let's prove this one. Let's prove this here. Orthogonality of this set S means U1 time U1 inner product U2 is equal to 0. U2 more U1 inner product U3 equal to 0. Blah blah blah. Shows that. So first of all, for arbitrary y in arbitrary subspace W, let's say y, define looks like this. Because y is the one of the vector in this subspace, so we have to find out this. There exists this coefficient. Then let's compute u inner product y inner product u1, which is equal to this one inner product u1. Right? Then due to the orthogonal array of the vectors, this one is going to be just the c1 times u1 inner product u1. c1 inner product u1 and u1. Since u1 inner product u1 is not zero, because u1 vector u is not non-zero vector, the equation can be solved for the c1 from here to here as well, at this. So c1 is equal to y inner product u1 inner product u1. This is the definition of the c1. To find cj for j is equal to 2, j is equal to 3, blah blah blah. Then compute y inner product uj and solve for cj. Then we can generally find out this solution. cj is equal to y uj over uj inner product uj. What does it mean? Why? First of all, why do we have to discuss this one here? Next, let me explain like this. Okay, so first of all, what was the subspace? Then which subspace we discussed so far? So, subspace. 자, 좀 설명해 줄게요. 여러분, subspace 우리 배웠던 거 가장 중요했던 subspace 뭐가 있었죠? 여러분, anyone? We discussed so many subspace, right? But there was the two very important subspace we discussed in midterm as well, right? 그쵸? Column space or null space, 그쵸? Column space or column space and null space, 그쵸? 그 subspace 안에 any vector y가 있는 자, let's suppose that we have a subspace W, for example, and in a subspace, and there is a zero. Let's say 0 here, and let's suppose that here is the one arbitrary vector y in subspace W, and if we have orthogonal basis for this subspace W, U1, U2, UP, more blah blah blah, then we already know this y should be described in a linear combination of the vector U1, U2, and UP. 그렇죠? We already know. The question is what this coefficient should be. So from this proof, coefficient C should be looks like this, right? Then the question is, what is the meaning of this one? What is the meaning of this one? Then how we can use this kind of properties to solve your Ax is equal to B. So first of all, okay, let's go back to the midterm exam. If there exists solution P should be in column space, right? P should be in column space. It means that P should be column space of A. P should be here. So should be here. Maybe 0 is here. Then should be defined. Draw looks like this. Then what was the solution? What was the solution? What was the solution for the AX equals B in this geometrical understanding? It was the linear combination of the each column vectors. 그렇죠? x1, a1, x2, a2. For example, xn, an equals 0. Then the question was how to find out x coefficient. 그렇죠? This one. Cj in this case y is equal to b. 그렇죠? y가 b고 얘가 이제는 컬럼 스페이스를 나타내는 코에피션트들 베이시스니까 Cj 코에피션트가 이런 식으로 풀 수 있다. 이게 kind of solution. This setting. We will see this one later, but I'd like to emphasize the importance of this question. Okay. Any question? So let's move further and let's go back to here. Okay. And we also have to discuss the orthogonal projection. Orthogonal projection. Given a non-zero vector u in Rn space and consider the problem of decomposing a vector y in Rn space into the sum of the two vectors, one a multiple of the u, the other orthogonal to u. What does it mean? Let's suppose the R2 space. Let's suppose we have an arbitrary vector y. Then the question is, we want to decompose this y to the y hat to z, but we want y as a we want to decompose y, origin y, to the sum of the two vectors y hat plus z, where y hat is the multiple of u, alpha times u, and z is orthogonal to u. So if u is here, it's going to be the orthogonal. So this is the way to represent y as a u on y hat plus z, where y hat is equal to alpha u for some scalar alpha, and z is the sum vector orthogonal to u. So first of all, there may be this kind of y hat and z, right? So first of all, if you already know y hat, then z is naturally be the y minus y hat from this one, this equation, right? So question is, if we can find out alpha, we can find out this decomposition. So the question is how to find alpha. That's the orthogonal projection. What does it mean? What does the orthogonal projection mean? Let's suppose that you have an arbitrary vector y, and let's suppose that you have another arbitrary vector y, a vector u. Orthogonal projection means you want to find out vector, this vector, that are multiple of the y. So it means that y hat should be same direction as u, and you want to find the orthogonal vector z in this case. So this u hat and z can be many kinds of decomposition methods. So this is just the introduction of the orthogonal projection. This kind of vector is called orthogonal projection. This is this one. So this orthogonal projection, this kind of vector is called orthogonal projection. So this vector determined by alpha. So question is how to find the alpha. Then we can find the projection of y on vector u. Okay, let me show you further. For any scalar alpha, given any scalar alpha, let's say that z is equal to y minus u alpha u. So that one is satisfied. One is here. This is the first equation. So this one, 그렇죠? Then z is orthogonal to u. Z is orthogonal to u. 그렇죠? By definition, if and only if 0 equal to this one, z, 그렇죠? Inner product u, inner product u, 그렇죠? Y from here, 그렇죠? Two vectors are orthogonal if the inner product is equal to 0. 그렇죠? 이것 때문에 그렇게 되는 거고. Then y inner product u minus alpha u inner product u is equal to y inner product u minus alpha u inner product u. 그렇죠? That is one equation one is satisfied with z orthogonal to u if and only if from here to here. If we rewrite this equation in terms of the alpha is equal to y inner product u over u inner product u. Then in this case u hat, which was alpha u, because alpha is here, u hat is going to be the y inner product u over u inner product u times u, right? U. Then this one is going to be the vector u y u inner product u times inner product u. This is the y hat. In other words, if you only know vector u and vector y, you can determine this y hat vector because this is equation with equation of the u and y. Then you can easily find out z because y minus y hat. Sure. That's the way to decompose your matrix, your vector y to the y hat plus z. In this case, vector y hat is called orthogonal projection of y onto u. Orthogonal projection of y onto u. This one. Orthogonal projection of y onto u. It's going to be the y hat. This is just definition. Just definition. It's not a difficult one. This is just definition. And vector z is called component of y orthogonal to u. Component of y orthogonal to u. Component of y orthogonal to u. What does it mean? Let me explain this one in Korean again. 자, 무슨 얘기를 하고 있는 거냐? 자, 이제 우리는 새로운 디컴포지션 시어럼, 자, ax equals b를 풀 거예요. 계속 이거 하고 싶은 건데, 이걸 더 잘 풀고 싶은 방법론에 대한 얘기에 대한 거를 이제 조금 중화사 이후로 가고 있어요. 그렇죠? 중화사로 가고 있는데, 첫 번째로 이제 그런 디컴포지션 메소드를 하기 위해서 orthogonal projection이라는 얘기를 해야 돼요. 이게 무슨 얘기냐면은 어떤 arbitrary vector u가 있고 arbitrary vector y가 있었어요. 근데 어떤 방법을 풀기 위해서는 벡터 y를 두 개의 벡터 썸으로 표현하고 싶은데 하나는 y 방향, 그러니까 u 방향으로의 프로젝션, 그러니까 뭐라고 내리는 거죠. u 방향으로 있는 이 벡터 y 핵과 그리고 z, u와 직교하는 z로 표현하고 싶은 거예요. 그래서 그 두 개를 합쳤을 때 y가 되는 yhat과 z를 찾고 싶은 거예요. 그때 이 yhat을 orthogonal projection of the y onto u라고 하는 거고요. z를 component of y orthogonal to u. 그러니까 y 중에 어떤 컴포넌트가 u랑 직표했는지를 z라고 표현하는 거예요. 이해됐나요? 조금 어렵죠? question. 자, 여러분 혹시 좀 이해가 안 되면 우리 질문 이해를 하면서 가야 되니까 우리 한번 질문을 좀 해봅시다. 전혀 이해가 안 되는 친구들도 괜찮아요. 전혀 이해가 안 되더라도 질문해 줘 볼까요? 혹시 이해가 되셨나요? 이해가 되셨나요? question? clear? clear? 정우? only 정우? others? 중간고사 이후로 보이던 친구들이 많이 안 보이는데 쉽지 않아요. 오케이. 마음이 아프네. 자, 이 다음부터 갑시다. 이 다음 where? which part? which part are unclear to you? 자, 우리 조금 시간 있으니까 좀 천천히 갈게요. 자, 지금 하고 있는 얘기들, 자, 여러분 우리 중국어서 봐서 알겠지만 막 증명 어렵고 막 한 거 아무 필요 없잖아요. 그쵸? 우리 증명하는 문제도 하나도 없었죠. 증명. 예, 너무 스트레스 받지 마요. 그러니까 제가 막 이렇게 증명해 주는 거는 정말 이렇다라는 걸 여러분한테 그냥 보여주고 싶은 거지. 여러분들은 이걸 이해하는 게 더 중요해요. 이 의미론들. 이런 증명에 막 너무 얽매지 말고 막 왜 이게 이렇게 되지 보다 왜 이게 이렇게 나오지? 보다 understanding, high level understanding. 무슨 의미를 가지는지 훨씬 더 중요해요. 알았죠? 지금 말하고 있는 것들은 우리가 이제 좀 이따가 어떤 디컴포지션을 얘기할 거예요. 다음 주쯤에. 그 디컴포지션 가기 위한 하나의 테크닉들을 배워가고 있는 과정이에요. 지금. 올소 오퍼레이션이라고 하는 테크닉, 뭐 미너 프로덕트라는 테크닉, 이런 테크닉들을 배워가는 과정이고 그 중에서 이제 올소곤 오퍼레이션이라는 컨셉은 어떤 벡터 u와 벡터 y가 있을 때 y를 두 개의 벡터의 썸을 표현하고 싶은데 그게 u 방향으로의 벡터 하나와 u와 직표하는 방향의 벡터 하나로 표현하고 싶다라는 게 이 올소곤 오퍼레이션의 핵심이고 그때 요 y 핵과 z는 결국에 u와 y의 이런 조합으로 만들어진다라는 거죠. 그렇죠? 어떻게 만들어? 이런 수식들을 따라가면 이렇게 만들어지더라. 라는 것까지만 일단 현재까지 이해하면 돼요. 됐죠? question. 그러면 u와 y 방향의 벡터면 그쵸. 아주 정확해요. 정확해요. z가 0벡터가 되는 거죠. 그쵸? 아주 정확해요. 이게 이제 무슨 의미를 가지는지 뒤에서 조금 더 설명할게요. 어쨌든 이렇게 그럼 반대로 u와 y가 직교한 경우는 어떻게 될까요? What if u and y are orthogonal? What happens? 어떻게 되겠죠? 그러면 z is equal to u, 그렇죠? 최대 네, 각도와 최대, 그렇죠? 그러니까 z is equal to u and y hat is equal to 0 and a is equal to 0, right? 그렇죠? 그게 되는 거죠. Anyway, this is just definition이죠. 그냥 definition이요, 그냥. 자, 따라왔죠? 조금만 더 설명해 줄게요. If C, 코에피션 C is any non-zero and if U, vector U is replaced by CU in the definition of the y hat, then orthogonal projection of y onto CU is exactly same as orthogonal projection of the y onto U. Then it means that if let's say here is a vector, okay, here is our coordinate and here is the vector y, and here is the vector u. Then if we consider the another vector, let's say cu, but also the projection, this one will be exactly the same. Will be exactly the same. It will be exactly the same. And hence the projection determined by subspace L spanned by U. What does it mean? It's just a line. Which line? This line. This line. So it means that the projection is determined by this line, not vector U itself. span of U. 그래서 Y와 이 라인과의 라인으로 이게 결정이 난다는 거죠. Force operation. Sometimes Y hat is denoted by projection L, Y, and this called orthogonal projection of Y onto L, where L is span of U. This one, this is L, and Y hat orthogonal projection. Orthogonal projection is equals to projection L of Y, which is equal to this one. Coefficient alpha defined here, determined here. So Y times U times Y equal to U equal to U, and U. Then we can find out this orthogonal projection vector. Okay. Let me show you example. Let's say Y is equal to here, U is equal to here. 7, 6니까 Y가 뭐 이렇게 있겠죠? 조금 이쪽으로 기울었겠네. Y, 그렇죠? And U 4,2, maybe here, 그렇죠? In this case, find the orthogonal projection of the Y onto U. Find the orthogonal projection of Y onto U. So, question maybe find out this vector Y hat. This is our question. Then write the Y as a sum of the two orthogonal vectors. One is span of U, 그렇죠? One is span of U, one orthogonal to U. So it means that Y hat, the question is find the Y hat and vector Z. So the question is just solve Y hat as a Y in the product U in the product U times U hat U. 그렇죠? So let's solve. What is Y in the product U? 블라블라 하면은 얼마가 돼요? 7 times 4 plus 6 times 2, so it's going to be the 14. 그렇죠? And U in the product U, it's going to the 4. This one in the product this one, it's going to be 20. 그렇죠? Then we can easily say that Y hat orthogonal projection of Y onto U is this one, and 40, 20, then 2, U was the 4, 2, so it's going to be the 8, 4. So maybe this vector is 8, 4. Then what was orthogonal? One orthogonal to you? This one. Z, 그쵸? Should be y minus y hat, 그쵸? y minus y hat. 그러니까 y minus y 그냥 계산해 보면은 어떻게 되냐면 y minus y hat은 7, 6 minus 8, 4, which is equal to negative 1, 2. 2. So this one, y minus y hat, which is equal to z, and y hat here, u is here, and this line is span of u. This is a geometric illustration of orthogonal projection concept. Okay? 그래서 뭐예요? 계산하는 건 정말 쉽죠. 어떤 arbitrary 벡터 y와 u가 있으면 우리는 그냥 이 식따라 계산하면은 이 orthogonal projection과 이 뭐예요? 이 u와 orthogonal하는 이 벡터 z 벡터 그냥 단순 계산을 찾으면 돼요. 엄청 간단하죠? 계산은 쉬워요. 의미를 이해한다는 거예요. 뭐예요? 그러니까 y를 벡터 u 쪽으로 직교화도로 떨어뜨리면 이 y 해시 되는 거고, 이때 우리가 이제 이거를 orthogonal vectors, orthogonal projection이라고 하고, 그거와 직교하는 애를 이제는 z라고 하는데, 이제 이걸 이렇게 표현한다. 이게 뭐냐? y가 u와 직교하는 성분이 얼마냐를 나타낸다고 했죠. 아까 orthogonal component라고 했으니까 그게 바로 z다. 이렇게 표현됐다. 라고 하는 거. 됐죠? 자, question. 계산은 너무너무 쉽고요. 그쵸? If calculation above the clock, then y hat, y minus y hat will be the orthogonal set. What does it mean? Y hat inner product y minus y hat should be inner product between them should be 0. So it's going to orthogonal set. Let's check, compute this one. 그쵸? 해보면 0이 나오네요. 그쵸? 그래서 since the line segment between y and y hat is perpendicular to L, by construct y hat, the point identified the y hat is closest point of L to y. What does it mean? What does it mean? So, what does it mean? So, let's go back to our high school. If there's a line, and if we have the point here, which is the most close, which is the closest point in this line? 자, 우리 옛날에 중학교 때 생각해 봅시다. 선이랑 점이 있을 때 가장 가까운 점이 어디예요? 네요. 수선의 발. 아, 진짜 오랜만에 들어요. 수선의 발. 그게 뭐예요? 수선의 발 어디예요? 요거잖아요, 요거. We already know that. This one. This is a closest point. So, orthogonal projection means finding closest point from vector y to this line, spanned by vector u. This is the university style explanation, but it's very, very simple and it's exactly the same to your knowledge. 똑같아요, 여러분들. 그러니까 뭐냐면은 y라는 점이 있어요. 벡터의 점이잖아요, 벡터가. 어떤 이 L이라고 하는, 즉 U로 표현되는 U로 스팬되는 이 L이라고 하는 이 라인과 Y와 가장 가까운 지점이 어디냐를 얘기하려고 하는 거예요, 지금. 그래서 orthogonal projection이 필요하거든요. 근데 가장 가까운 라인이 뭐냐면은 결국에 이거였어요. orthogonal projection. 지금 내려서 직교했을 때 요거 찾고 싶은 거예요. 그래서 그때의 요 벡터는 결국에 이거였던 거죠. 그렇죠? 그래서 결국에 이걸 왜 하느냐? 이 Y와 어떤 이 스페이스 사이의 거리에 대한 얘기를 하려고 하는 거예요. 나중에 얘기할게요. 개념 이해되죠? 그냥 어렵게 영어로 쓴 거예요. 개념은 너무너무 쉬운데 벌써 우리 다 알고 있는 얘기인 건데, 그렇죠? Any question? 질문 있나요? Let me go further. We discussed the also corner set, right? And there are also normal set as well. Also normal set as well. What is also normal set? It's very, very similar to also corner set, but the main difference is that this set is an also normal set if it is the orthogonal set of unit vector. So what was the unit vector? What was the unit vector? If length of the vector is equals to 1, 그쵸? Then we call this is a unit vector. That in this case, in this set is called also normal set. also normal set. 그래서 뭐 이렇겠죠? orthogonal 셋 안에 also normal 셋이 있겠죠? also normal 셋이 있겠죠, 뭐. 그렇죠? 이렇게 있겠죠? 왜냐하면 벡터가 유닛 벡터인 경우가 이렇게 표현되니까. 네, 그렇죠? If W is subspace spanned by a set, such a set, also normal set, then this one is an also normal basis. 그렇죠? Same definition of also normal basis. In this case, also normal basis, since the set is automatically linearly independent. 그렇죠? Because they are also normal set, also corner set. 그렇죠? The simplest examples of also normal set is standard basis. 그렇죠? 뭐예요? 우리 맨날 얘기했던 거. 1, 0, 0, 1, 1, 0, 0, 0, 1, 0, 0, 0, 1. The standard basis is the simplest example. 그렇죠? 이런 거 이제 also normal set이라고 한다. And any non-zero subset, this one is also normal too. So 뭐 non-empty subset of this one, 그렇죠? 그러니까 이거의 subset도 also normal이다. 왜냐면 이걸 만족하니까. 이런 얘기예요. Let me show you an example. Show V1, V2, V3 is also normal basis of the R3. Also normal basis of the R3. So we have to prove they are orthogonal each other and length of each vector is 0. 1. 그렇죠? So first of all, let's compute the length of V1. 뭐예요? 이거 어떻게 되지? Scale root 3 over scale root 11 plus 1 over scale root plus second here plus 1 over scale root here. If you compute this one, 9, 11, 11, 그렇죠? 1, 그렇죠? You can similarly prove, similar compute, prove V2 is equal to 1. This is V3, 그렇죠? V3 is equal to 1. And let's prove V1, V1 in the product V2 is equal to 0. And it means that they are orthogonal each other, perpendicular each other. Like this. Let's prove this one. Let's go just compute this one. How? From here. So V1 on the inner product V2 is going to be the 2, the 0. V1 inner product V3 is going to be 0. V2 inner product V3 is equal to 0. Please check that if you want. So V1, V2, V3 is an orthogonal set. Orthogonal set and orthogonal set. And from here, they are also normal set. also normal set. 그렇죠? Since they are 그렇죠? 여기서 바로 증명했네요. 그래서 also normal set. 그렇죠? 방금 했던 건 얘기죠? 그렇죠? 그래서 since the set is linearly independent, 그렇죠? Because they are also corner, 그렇죠? They are linearly independent. Then these three vectors form a basis for the R3 because they are linearly dependent. Basis for R3. Why? By invertible matrix theorem, 그렇죠? 이거에 의해서 얘네가 베이시스가 된다라는 거예요. 그래서 요 V1, V2, V3가 무슨 얘기냐? 얘네가 V1 이렇게 생긴 V1, V2, V3 방금 말한 그 성질에 만족하는 그러니까 길이가 1이고 걔네들이 다 올소고날한 애들 각각이 직교한다는 거예요. 각각이 올소고날 each other 이렇게 생긴 애였으면 이게 베이시스다. R3다. What does it mean? Any vector in R3 space, let's say Y, can be uniquely represented by these V1 and V2 and V3. Okay, so one of the very simple orthonormal basis was the 0, 1, 1, 그쵸? 1, 0, 0, 0, 1, 0, 그죠? 스탠다드 엘리먼트였죠? 0, 0, 1인데 this V1, V2, V3 can be a new coordinate. Can understand where we can understand Y. Because any vector Y in R3 space can be represented by V1 and V2, V3 as a linear combination of V1 and V2 and V3. 그래서 뭐예요? 자, 이게 무슨 의미를 가지냐면은 얘가 올소널 베이시스면은 우리가 축이 뭐예요? 아까 1빵빵, 빵1빵, 빵빵 0이라고 하는 걸 우리 항상 표현하잖아요. 그렇죠? 그 축을 얘를 생각할 수도 있는 거예요. 축을 트랜스포머 할 수 있다는 거예요. 그렇죠? Y는 똑같이 Y지만 어떤 베이시스로 나타낼 때가 달라지는 것 뿐이겠으니까 축을 트랜스포머 할 수 있다는 거예요. 그렇죠? 이게 어떤 의미를 가지는지 우리가 뒤에 설명할게요. When the vectors in orthogonal set of non-zero vectors are normalized to have a union length, then new vectors will still orthogonal, so hence the new set will be the orthonormal set. What does it mean? If we have arbitrary U1, U2, and U3 orthogonal vectors, they are perpendicular to each other. It's not this one. But if we normalize U1 and U2 and U3 to the V1 and V2 and V3, then length of the V is 1. Then it's going to be the orthonormal set. 그래서 어떤 올소고널한 셋은 그냥 유닛 랭스로 노멀라이즈 해버리면 그냥 걔가 다이렉트하게 올소노멀 셋을 쓴다 라고 하는 얘기예요. 당연한 얘기죠? 그렇죠? 자, 오늘 여기까지 할 건데 혹시 질문 안 되는 이해가 안 되는 부분이 있으면 좀 질문해 봅시다. Question. Question? No? Okay, so that's it. So because today discussed so many concepts, we will stop here. And if you didn't fully understand orthogonal or orthogonal projection or orthonormal concept, please recap. Please recap the our recorded video. I will upload recorded video soon. So please recap and let's move further next week to discuss the new decomposition, matrix decomposition method. Okay, we already discussed the factorization method. Was the LU factorization, right? But next week we will introduce another factorization technique, dual factorization, which is a much powerful way to understand your matrix A. Okay, then that decomposition method requires the knowledge of the orthonormal sets. So that's why we start from here. So please recap. 그래서 이제 우리가 다음 주가 되면 우리 LU 팩토라이저 하나 배웠죠? 이번 학기에 한 3개 정도 배울 건데 LU 팩토라이저가 좀 더 강력한 이제 테크닉을 배울 거예요. 팩토라이징 테크닉. 거기서 이제 이런 컨셉들이 있어요. 여러분 혹시 오늘 좀 이해가 안 됐던 부분들은 제가 올려줄 테니까 잘 공부해보고 우리는 다음 주에 다시 봅시다. 알겠죠? No more question? Okay, that's it. So this is end the please lecture and please recap. 그렇죠? And thank you very much and see you next Tuesday. 자, 여러분 오늘도 너무너무 수고하셨고요. 복습, 알겠죠? 꼭 복습하시고 우리 다음 주에 봅시다. 고생하셨습니다.